Hi, this is Traxi, Computer Science. This is part 2, Computer Science Foundations. In part 1, we looked at data structures, algorithms, and the complexity arriving with storing of data, accessing the data, and so on. Today, we are going to understand how every AI product is part of a distributed system, and model is just one component sitting somewhere deep inside. So, let's get ahead. What we need to understand is while we are talking about AI product, and if we talk about its performance in terms of the latency, the cost, reliability, it's not just dependent on that AI product alone. Yeah, the surrounding system or the model that sits in that environment, the whole environment contributes as a whole to these parameters. And most of the time, these parameters are not because of the LLMs or the model. It is because of the other layers that are sitting and deciding on how to serve the data. Okay, and why is this important for a PM? We need to understand that whenever a engineering team or a customer success team or a customer says that, hey, a particular feature is slow or wrong or expensive, we need to understand the whole trace. We need to understand the whole network uh, that the data has passed through, from the users clicking on the request until the response comes back, to understand where the system is not performing. And we can only debug this if we can understand the whole layers. If somebody says it's slow, it has no meaning. What we need to understand is, hey, we are making 400 database calls per request and hence it's slow. So as a PM, understanding these layers of data movement or request and response movement is very important. So we are going to look at this in 4 parts. First, we'll understand the whole map where the latency or hierarchy sits, and then we are going to look at how the request travels inside. And there is no single layer where we could say that, hey, something is failing. We need to unwrap 4 layers of that, for caching, for scaling and load balancing, sync and message queues, and look at observability. We need to understand where this is failing. And this is only possible if we understand all this. That is, we understand networking, how the request travels from the moment we click the button until it goes to the LLM, comes back as a response. We need to look at architecture. What are the various elements or components of the system that receive the request and how it is routed at various levels. We need to understand databases. Hey, are we using a structured query database, or are we using a non SQL or a document style or a vector style database? We also need to understand, hey, whether the data is indexed in the first place or not. Yeah, and the drill that we need to follow to understand why something is failing. Finally, the compute and the operating system where all of these run. Yeah. Finally, we will end with the fourth section where we are putting it all together. First thing that we need to understand is what is the layout of the environment, or if you could call it architecture. How how are the various components laid out in the whole system. And we need to see the complete request flowing into it. Only then we will be able to understand the flow of the data, and we also will be able to measure, hey, when the data travels from a particular point to another point or component to component, where is it slowing down. Yeah, and that's the point we will understand which particular component in the whole of the system is slowing down or hitting on the performance. So this is where a typical example looks like. And in this, if you see, if there is a user in front of the system, he's typing something, he's clicking on a ChatGPT tool, and he enters a query and hits enter. Typically it would start with an API gateway where HTTP request is flowing through. It goes to a DNS server, and then there is a transport level security that needs to package the whole data, and then it needs to send. and it goes to the ChatGPT reply service that which detects, hey, do I need to query this with some database? Based on the database, there is some latency. It pulls the data, it sends it to the model that is serving, and in the end, there is a GPU, the physical layer on which the whole compute happens. And once this happens, the tokens are streamed back to the user through the model that is serving. So uh, while we will dive deep into each of these components, we need to understand that, hey, the model or the model running on the GPU is only one part of this 6 or 7 line story that we are going to look at. And it's only one line that we are looking at, but we need to be wary of each of these lines that serve other purposes. And if we are talking about latency, cost, and reliability, all of these lines needs to be looked at as well. Yeah, let's imagine you're talking about a latency. Yeah, there is a slowness in certain layer. So how do we measure each of these layers? So every layer has their own rough calculations of the time it takes to process. For example, if it is CPU or cache or register, it takes approximately 1 nanosecond. If it is a RAM access, yeah, the moment you try to access the RAM and for it to give response, it takes approximately 100 nanoseconds. It's here itself, it's multiplying by 100. Yeah, from CPU to your RAM, this itself is 100 times multiplied. Then SSD read, if you're reading from a chip or a file system in your laptop or a server, that has 100 microsecond latency. If you're looking at a network round trip, for example, if you when we talk about the regions, it could be server regions or it could be geographical regions also. So there it's around zero point 0.5 millisecond. For example, currently I'm running one of my website and Amazon services, and this AWS sits in Mumbai, and it's in the same region. I and the Amazon server, AWS server are in the same region. So the latency is around approximately zero point 0.5 millisecond. But if you take or access a website that's running in maybe North American region and it's cross continent, so the latency could add uh, by approximately 150 milliseconds. Yeah. So what we're trying to say is the closer we do something to the CPU, the faster it is, and the farther we get away from the CPU, the more latency that we are going to add. So when um, when we do designing of systems and we say, hey, just fetch the data, yeah, imagine if there are 50 times a request, it's going to do 50 trips down this ladder. Yeah, and that's why just running down this data is not the ideal solution. Maybe we'll have to cache it. Yeah, we need to reduce the round trips as well. And that's where the layers come into picture. If we do not understand the layers, we will not be able to design the systems properly for latency, cost, and reliability. Yeah. And we are going to look at how one request travels, and we'll unwrap it. We'll go request inwards, that is, we'll start with the network, we'll go into architecture, data, and the compute finally. So imagine the request is traveling, and typically, many a times, network is the bandwidth issue. Our network or the bandwidth issue exists, and there is a set floor. Yeah, and request lifecycle typically looks like this. Yeah, there is a DNS lookup that happens that tells, hey, uh, to which server do I need to send the request to? TCP or transport control protocol or transport layer security needs to do a handshake. Then it needs to do a HTTP request, hypertext transfer protocol request, and then it sends it to the server that is going to process the request. And similarly, it will have to follow back to us and give a response. Yeah, every AI product is HTTP to APIs. So bad latency often lives here. Yeah, some of this layer, not in the model. The model is going to give you number of tokens per second or a number of queries per second to be processed, but your network layer could be one of the biggest bottlenecks. We also need to look at latency versus bandwidth versus throughput. Yes, a latency is one round trip. That is, you give the request, the system gives the response. The duration between the request and response is the latency. Imagine if you are talking about bandwidth. Bandwidth tells us how much data can pass through a particular layer, and it could be seen as a pipe. For example, how much water flows through a pipe. We would typically measure it in cubic volume, like cubic liters, and here it's data per second or GBs per second. That's the bandwidth. Throughput, we are talking how many requests can be processed per second. So all the three are totally different, and we need to treat them accordingly. If you're talking about LLM streaming, that's a latency trick, because the moment it starts identifying the tokens to give you, it starts streaming to you, and hence your perception that, hey, I'm getting better speed is pretty much visible. And actually it's not changing the total generation time. What it's giving you is tokens on the fly, so you feel, hey, it's faster. And why the network is often the floor? Imagine a model generates 800 milliseconds behind three 150 millisecond hops. So you're adding three 150s milliseconds, which is 450 milliseconds. 800 plus 450 milliseconds, which is 1.2 seconds experience. Here itself, half a second of latency is added just because of three hops, and that's why it becomes the floor for you. Beyond this, you cannot improve the model's speed. Also, even if you try improving, there is a 450 millisecond latency because of three hops here. Yeah, hence edge deployment, regional endpoints, and caching is sought as a solution here. And for us as PMs, this is the most important question. Hey, where does the time actually go? We need to think through this, because almost every time that we say that, hey, the model is slow, it might not be the model that is slow, it might be the network. Yeah. So moving ahead, there are different types of uh, abstractions that typically happen and systems that are built, and many of this could also be leading to latency. For example, the services that are built could be monolith versus microservices. Monolith is one huge deployable app that is built. It's rigid in nature, that is, it's hard to scale as a single hot part, but it's simple in nature because everything is set together. Whereas microservices, you split everything into smaller services which are independent of each other and relate over the network, where each scales and deploys separately. Yeah, but the challenge here is that it comes at a cost of distributed complexity. Imagine one service failing, you'll not know whether the other service is going to depend on this. Is that also going to fail or pass? So that becomes a little bit challenging in microservices, but the scale at which you can build microservices is much more easy and faster compared to monolith. APIs and the contract, this also changes. Imagine you have to give a request and get a response. APIs, typically with all the ChatGPT and everything that we are doing over the internet, is through APIs, and most of the times we use REST services, uh, where a REST format of contracts are done over HTTP, and that's that was so far good, but Google brought in RPC, remote procedure calls, and these seem to be faster than REST resources over HTTP, and they are typed and service to service contracts. So these are pretty faster these days, and increasingly everybody is moving to gRPC. You know, for anything that's platform shaped, APIs are the product. Imagine there are APIs that help you get the data from a particular website, like weather website. So there the product itself is the API, or the API itself is the product. uh, what happens is, when you build an API as a feature, it lives within a product and you use the product. For example, if you're using ChatGPT, the APIs are not the product here. You're conversing, so the product is the chat conversation. But if you're a developer and you use certain APIs to make the calls, their API is the product. since you're using APIs to build your own product, and ChatGPT is selling that API as a service, or the product. Okay, what makes an API good? We need to ensure that there is graceful failure. There is enough timeout. The number of retries that can be done is set. Fallbacks. What happens if the API goes down? What happens if the API doesn't give the response? What happens? Idempotency. If you're trying to do something and it doesn't work, or it happens twice, we need to avoid double charging. So it should be safe to retry as well. So what happens with idempotency? You need to be very clear about it. Versioning. Don't break the callers. Imagine you're on the version 1 and certain people have uh, built their products on version 1. You need to ensure that there is a proper roadmap to sunset that version 1 and migrate the users to version 2. You cannot just overnight migrate to version 2 and expect everybody to use version 2. So versioning is also important. Putting in rate limits to avoid consumption of too many resources by one particular system. You need to put in rate limits and a defined error contract. Many times APIs are built without proper documentation and error contracts, so users of that APIs do not know why a particular services or API is failing, and that becomes a big challenge. Yeah. And remember this, API is half the drill. Yeah, what happens to the caller when this is slow or down? We never talked about that. So is it idempotent? How is it versioned? All these factors are important. While API is available, you need to think through all of this here. An API that ignores failure and versioning is a future incident. Yes, it's definitely going to happen. That brings us to databases. Typically, we have two types of databases that we are going to build AI products on: SQL and NoSQL. While vector databases are there, they are typically in the NoSQL side. And how do we pick a particular database for AI products? That's a that's a 3-hour lecture of its own. We're not going to get there, but we're going to understand what is it required. So what is the typical difference between SQL and no SQL, or no structured query language? While there is some structure, okay, uh, examples of SQL or relational databases look like Postgres, MySQL, and so on. NoSQL is typically document structured or key value paired. So the MongoDB, your DynamoDB, Redis, Cassandra, all of these live in this space. Your vector DB is like, hey, why am I not getting it into my mind? All the vector databases like, hmm, all the vector databases come into this space. We're going to look at a few of them. For example, VectorDB provided by Postgres, VectorDB provided by Mongo. All of them sit here. The databases have a table structure here. They have a fixed schema, and they are typically in rows and columns because they are structured query databases. Whereas here it's typically document. When I say document, it could be a JSON, it could be a XML, any of that. They are typically also like key value structured databases. Redis is a good example. Your cache, all of them have key value pairs. A white column in nature, as in key is a um, key tells what index the value exists, and values are typically white column. When I say white column, it does not have a limit. The document structure can extend into MBs also sometimes, not just kilobytes. And sometimes it is graph in nature. All vector databases fall here because they have a graph structure. Strength, they are their strengths of SQL is they are good in relationships. You can build good relationships. They have a strong joins, and they support strong consistency like asset structures, mm, atomic consistent and all of that. Here it can scale faster. There is flexible schema and high write throughput. The ability to write data faster is one of the most sought after feature for NoSQL databases. This we use when we want structured and relational data. Correctness matters for systems like payments, orders, etc. Oh, okay, it's cut off. but typically it's for payments, orders, all of that. All banking systems typically use structured databases, and NoSQL databases is typically used when we want huge scale. The schema is always evolving, and we want a simple access. AI era relevance. This is still the backbone of most of the products when we want to store huge volumes of data. OpenAI still uses Postgres in the backend, and for some of its data to be stored. NoSQL vector databases are being highly used for embeddings as a framework. The principle underneath the choice is that, hey, pick the data model that matches your access pattern, not a better database. Don't ask, hey, which is a better database, is Mongo versus Postgres. It's never. It You need to identify what your access pattern is and use the right database. The vector database that we typically use is for embedding purpose. Yeah, so if our use case is to find the most similar vectors, I don't have to go to relational database, I have to go for vector database. And not just putting the data in, taking the data out is also a huge question or challenge. So in that case, we need to look at, hey, have I indexed my data correctly? Indexing helps you fetch the data faster from a database, and instead of you scanning through every row, if you had indexed the data, you will directly jump to that record and fetch it. So instead of going from O of n, if you remember the order of n as a big O notation that we used in the whole of week 1, we are saying it will reduce from O of n to O of log n. Imagine millions of records, you'll have to traverse through millions of items. But here but here it is not the order of millions. It reduces by the reduces by half every time you traverse. So to reach 16, we need to hop only 4 times, so on. So it dramatically reduces the number of jumps that we have to do when we have to get a data that is indexed. Normalization versus denormalization. How smaller do you fracture or break the data into so that it sits in the database and you are able to store them separately as a fact, and when you're reading, you use joins to read the data. Do you need that, or do you need faster reads? So that's the question. So do you need faster read, or do you need write simplicity? That's the trade that you're doing. Transaction and acid uh, framework that's used for transactions. You, you need to know that if the transaction needs to completely process, that is all or nothing groups like debit and credit, never do partial things, then you need to go for a SQL kind of a database. If it is distributed, this will get expensive because you will have to write in multiple places, and you also need to understand eventual consistency. you know Eventually, will the data be consistent across systems? So the drill of schema review typically looks like this. When in a database, when you create the schema, you need to understand, hey, what's the main read path? Is it indexed? This is denormalized. What breaks when duplicate items drift? Expected row count in a year. In a year, how much will the data grow? Which operations must be atomic together? What personal data is here? Deletion or retention requests can be placed. Everything that has to do with PII will have a challenge across GDPR, CCPA, and other compliance requirements. And this is where the model actually runs, which is on the OS level. Okay, at the OS level, our biggest challenges are across these three. One is process versus thread. Okay, a process is an isolated program with its own memory, and a thread is a lighter path in its inside it. Okay, which is sharing the memory. So we need to build multi-threaded applications that are sharing resources to get a task done instead of a single threaded nature. But this would mean that it's sharing the same resource, and they will be competing for that resource. So it doesn't mean that if you have 8 cores, it will be 8 times faster. Yeah, you need to look at the size of the thread that's being run, and how much compute it has to do of its own. We need to understand the difference between concurrency and parallelism also. Concurrency is, imagine there is one cook and he needs to cook many dishes. So what is he going to do? If he's doing it concurrently, means he's doing dish A, he's jumping to dish B, then he's going to dish C, and so on. His time is split between these three. What happens is, while he's making three, he's not completing any one at the same time. With parallelism, imagine there are three cooks and they are cooking each of the dish separately, and all the tasks run at the same time on different resources, and hence it completes faster. So that's the difference between concurrency and parallelism. Memory, RAM versus disk, and GPUs out of memory. Yeah, OOM stands for out of memory. So RAMs are typically fast, but they are smaller in size. Whereas if it is a disk, it is slow in nature but is large. Typically, you would have seen in your laptops that RAM sizes are anywhere between, these days at least, between 4 to 32 GB or 64 GB, whereas disks start anywhere between 128 GB to all the way to 2 terabytes. Yeah. And GPU going out of memory is typically a compute problem. And what you need to ask is, hey, a model that doesn't fit in GPU memory can't run. So how much larger should my GPU be? That's a question that we need to ask. And one of the topic that we learned in quantization, that is reducing from a 32 floating point uh, weight to a 16 floating point, or 8 float point size for the weights, typically reduces the model size. And that brings us to the next most interesting part of this part 2, which is the 4 wraps. Yeah, we're going to understand that the systems don't live at a single layer. They live in multiple layers, and that's what we need to wrap all of them properly. Imagine we have a limited memory, and how much we can take in versus give out is very limited. So we need to understand where will that memory sit in. So many a times we have to move the query time to the build time. Yeah, we'll have to pay once to compute, serve the copy free until goes stale. That is the whole concept of caching. Okay. And where does this cache live? It lives in our browsers, it lives in our CDNs, it lives in memory cache databases like Redis, Memcached. It lives in database query cache layer and multiple layers. So whenever a request for a website is made, some of those elements are pulled, and they are cached in our local browser's memory, so that our memory, our database, so that when next time the database request is made, it doesn't go to the entire server, to the server, and bring the entire website again. It fetches certain elements from the database and refreshes the page based on that also. CDNs, the content delivery networks, the closer they are in the same region, they are cached memories. And database cache, query cache, every time the same query runs, the same data is returned. Imagine the load on the database. So we query such caches, we cache such queries, and their results in a cache layer, and we serve it from there, which is much faster than doing the query on the database. And the one metric that we need to keep a track of always is the cache hit rate. If our cache hit rate is 40%, it means we are doing 40% lesser calls or fewer calls to the database, to the CDN, to the app cache, or it could be any of that. And that's a very important metric. Yeah. And here is the strategy that we could use. Imagine we are using cache aside, as in every time a database update happens, we take certain data, a query is made on that database, we take that query and the results, and we cache it. That's called cache aside lazy. So this is simple. First request always misses. Yeah, first time that the call is made for a particular, or a query is made, we will never have the cache data. So what we would need to typically do is, we'll have to query and then index. There is something called write through. If a data is written, yeah, and we immediately index it, the reads are fresh. Yeah, writes become slower because we have to write the data and then cache it also. A write back is the other way around, where we do a fast writes, and we lose risk before flushing of the data, because um, data becomes sometimes stale as well. So imagine there are two topics that we need to understand, that is eviction and TTL, which is time to live. Whenever we evict the data or remove the data from cache, which is based on least recently used data, uh, if the time to live is shorter, uh, the data will be fresher but will have a low hit rate, because uh, a, a query data that was not having a short time to live would not be found, so the hit rate would be lower. A long TTL means uh, the data that are even less frequently queried still exists in the cache. This would mean that it has a higher hit rate, but this would mean a lot of stale data exists in the cache. Yeah, so that's a trade-off that we need to do. The hard part is the invalidation part, where we are saying that hey, a cache is a copy that we know. The original data sits in the database. A cached layer keeps a certain part of that in memory, so that it can serve faster. So when a cache is a copy, and when the source changes, the copy is wrong until invalidated or resynced or recached again. So the KV cache that we are talking about, key value cache, the prompt prefixing cache, the semantic cache that we spoke in part one, are all this applied to inference layer. Okay. And if you want to serve more requests, what we can do is, if there is a system, you can either scale up, make the system bigger, or you can scale horizontal, which is scale out. We can add similar machines and put a load balancer on the front. So what is a load balancer gonna do? Load balancer is gonna spread the request and run health checks consistently. And if there are any instances that are dead, it's gonna pull those dead instances and remove them. And how are the serves request? They are through robin or least connections method. Round robin goes saying that hey, once I've served here, next I'll serve here, next I'll serve here. In the least connections, the load balancer will check, hey, 50 requests have gone here, 51st request is coming, it checks here, here is only 10 requests being served, so it sends the next request here to avoid loading on only one machine. So what are the strengths and limitations? This is simple because you don't have to change code. You just have to increase the RAM size. You just have to increase the memory and so on. Whereas in horizontal scale out, this is elastic in nature because you can keep adding machines, but it also means that you will have to make some code level changes. This also becomes fault tolerant, whereas this is a single point of failure. This is not a single point of failure and becomes fault tolerant. This has a hard ceiling. Hey, how much GB can you actually add in a machine? There is a ceiling to that. Yeah, but this becomes a single point of failure, whereas here the limitation is that it needs statelessness. You need to write the code such that these are stateless, these do not store any state, so that a request that goes here or here serves the data from the same database. And AI era reality is about the GPUs. Okay, imagine these are GPUs. Okay, and you are requesting here. The companies would have put in a lot of money to purchase these GPUs, so they can't sit idle. Yeah, and if you have to turn out another instance, these GPUs are in GBs of sizes. The models are in GBs, gigabytes of sizes. So for them to copy, bring that system up, it takes a lot of time, which we call as cold start. And that's why the problem of serving efficiency becomes very critical in AI. Each GPU ideally should be optimized to serve as much as possible always. Otherwise, never add GPUs. Adding more GPUs will not serve the purpose, because if the request is low, query per second is low, you'll be wasting a lot of system capacity, and GPUs are costly. If they are sitting idle, you're burning money. And that's what we do of coupling work from the request. Okay, imagine a request comes in, you don't immediately serve it. Rather, what you do is you decouple the work from the request and you put it in a queue. Okay, and when a worker is available to process that, it picks it up and processes it. What this does is this has three good wins. It helps absorb the spikes. So suddenly imagine there are 50 requests coming in. Instead of processing all of them, you just put them in a queue, and whenever a resource becomes available, it delivers the value. Improves resilience. Yeah, a dead worker's messages, they will keep waiting until a next worker picks it up and resolves it. It decouples deploys. When a producer and consumer are able to ship this independently, we have a better chance of building systems that are reliable, easy to integrate, and so on. So decoupling the deployment is also one of the good features where asynchronous messages or queues win. Some queue systems that are built recently are have been there for a while are Kafka, simple queue system by AWS, RabbitMQ, then we have Celery, all of these, Rabbit Message Queue, and so on. Yeah, but the challenges also exist. What are those challenges? Most queues are at least once, as in you have to send the request at least once. So the workers must be idempotent. You remember the property that we talked about in idempotency? You should not have double charging. Yeah, if you're running the request twice, okay, and the message that keeps failing lands in a dead letter queue. So a request that keeps failing will be put to a dead letter queue and it will never be processed. So these are some challenges, okay. And most of the AI workloads these days are asynchronous in nature, because whenever you send a request, they don't go directly to the system or GPU for LLMs to be processed. They don't go to the LLMs for them to be processed at the GPU level. Rather, they are batched together and sent to the GPU so that GPU's utilization is consistent. high uh, high GPU utilization happens. Okay, so embedding backfills, batch inference, eval jobs, RAG ingestion, long running agents are all AI workloads. Imagine you wanted a 2-minute generate this report request. Okay, ideally it will not hold an HTTP connection. Yeah, and it'll do enqueue and it will notify back saying that I have put it in the queue. The inference request queue from part 1 is the same idea as the GPU. You remember, queue is nothing but first in first out. You're standing at the Starbucks coffee, you're first in the line, so your request gets served first. Last but not least, the observability layer. You need to understand, hey, where is my data request flowing through, what's happening with that request, where is the latency, where is the cost, and how reliable are these services. These are the three topics we discussed from the beginning. Okay, so imagine we can see them as three pillars. For example, logs. It tells you what happened. A certain request, whenever it's processed through a system, we log all the data accordingly. So if a customer raises a request, we can understand what happened there. Metrics. Imagine we tracking queries per second, error rate, and latency percentiles. This help us understand the performance of the system in simple metrics. Traces. Imagine you want to trace a particular request that failed, and trace will help you. In AI, traceability is the biggest challenge today, and if not documented and logged really well, identifying why a certain refund was made for $500,000 or $50,000 or even $5,000 will become a huge problem. We need to solve that at design level, not at build level. Distributed tracing. Hey, I have a request coming in. Where does this latency happen? If I have to trace it, I need to understand how much time was spent at gateway, the database level, the vector store level, the model service. 400 milliseconds here, 900 milliseconds there. I need to understand the distribution of time across all these elements. This is typically turning the anatomy from a diagram into a diagnosis. Yeah. The percentiles are not averages. Yeah, we spoke about this, why averages are pretty bad when it comes to large volumes. Ideally we should look at percentiles and understand if you're going to target p95 versus p99 kind of a percentile, and set that as the service level objective per layer. For each of the layers that we discussed so far, at each of the level we need to set certain thresholds or objectives. uh, the intro's 400 dB calls per request, a loop firing one query each, 1 plus n instead of one batch query. Yeah, that's the n plus 1 query trap that we were discussing so far. And if it's not obvious in a trace, then it becomes invisible in review as well. Yeah, the AI adds new metrics, yeah, tokens per request, cost per request, cache hit rate, time to first token, queue weight. All of these are important. Yeah, the evals that we are running are actually offline observability for quality. So every time we ship something, we need to ship it from the angle of observability. Let's put all the things together and understand what we have learned so far. Yeah, this is us returning to the map, and we are annotating, and we are understanding with some real numbers on every hop. Imagine the user has clicked, the request goes to the network, and there is a HTTPS call being made to a particular API gateway. This could take anywhere between 50 to 150 milliseconds for API gateway to respond. In architectures, typically the gateways route to a particular service, and that service could do a database fetch. And these database fetches could be anywhere between 5 to 20 milliseconds, to vector databases where it's 20 to 50 milliseconds. Yeah, and if you are looking at the architecture, the services will typically called model serving. The model serving can take anywhere between 500 to 1500 milliseconds, which is 1.5 second, for the model to run and give back the answer. Once it comes, then we need to stream the tokens back to the user. That could take a few milliseconds of latency. Yeah, what you need to understand from whole of this session is, here, model run, our model's performance is one line item in this 7 line layer. So that's the most important part. So instead of saying which model or how fast is the model, we should be asking, hey, how fast is my entire layer, or sorry, entire request response time, and then split that into each of these layers separately and understand which layer is performing poor, and then improve on top of that. Do not go to directly improving the model's response time. That's a rookie's mistake that we will be making. And from a PM's angle, here is something that's important for PMs. Okay, most model is slow problems aren't the model. It could be network hops, it could be unindexed queries, it could be missing caches, the whole architecture could be wrong. Yeah, we will only debug what we can name, so we need to ensure that we understand this vocabulary very clearly. The schema or API review builds trust, so we need to interrogate a schema and understand what API contracts are written there. Yeah, that will earn a seat at the design table. Yeah, and that's very important, because without understanding these, we cannot go and talk to the engineering team or design team. We need to understand access patterns, drive data choices, how you're going to access the data, put the data, take the data out, what kind of queries you're going to run, uh, how's the data related with each other, what kind of idempotency do you need, um, do you need faster reads or faster writes. All that will decide your database choice. The latency hierarchy is a cost and UX map. How? Because it will tell you where to spend effort and why streaming helps perceived speed. So imagine you want a very good experience of returning response to a request sent via ChatGPT. Streaming solve that problem. Instead of shipping the whole response after 5-10 seconds or even minutes in long reasoning queries. What they did was they streamed the data immediately, so it tells you that hey, it's thinking, it's giving you the initial tokens as a response. So you are always experiencing the fastness of the application. You immediately see few tokens coming in, so you think the system is responding faster. So that's where the cost and the UX map are important. Okay, here are some misconceptions to avoid as well. Slow feature doesn't mean slow model. It could be network, it could be your database, it could be cached layer, or any of that stuff. No SQL is better than SQL. No, your access pattern defines which is better for you. And index is free. No, it also has some challenges, and it could help with read speeds, reducing cost for storage, but it will always slow down the writes. Yeah, microservices are professional. Uh, they buy scaling at the cost of complexity. So a monolith is often right in the beginning, but as we scale, we need to look at how to break that down and build microservices. Streaming makes the model faster. It's your perception. Actually, the total generation time remains unchanged. It's just that it's shipping you some tokens early for you to have a better user experience. And here is the interview prep for track C, part 2. Now, some of these questions could be asked in a AIPM interview. At this point in time, I do not know. This is what I figured out through my experience. One question could be, hey, walk me through a user clicking generate. Could be image, it could be text, code, any of that stuff. So our request typically goes through HTTPS, does a DNS lookup, or a transport layer security is validated, then it goes to a gateway. Gateway routes it to a particular service. Service reads an indexed database, looks up your past memory, collects that memory. It's typically or often a vector database, and then pulls all the required information. It gives to the model, and in model, before it's served, it stands in a queue, and where multiple requests are batched together, it is sent to a GPU for processing, on which the LLM is running. And once the data starts coming out, we stream it back to the user. So the model is one of that step. Rest all is what we discussed now. Should we use SQL or NoSQL for a new feature? It should be defined by the access pattern. If the priority is on relational and correctness of the data, then we need to look at SQL with acid nature and joins. If it is massive scale evolving schema and simple lookups, NoSQL would do the job. If you're talking about embeddings, where we need to understand the distance between vectors, semantic search, and so on, a vector DB would be much better. What would you look for in a schema review? Ideally, I would look at indexed read paths. Hey, the data exists, but have we indexed it? Without it, it will do a full table scan, which is slower in production when millions of records exist. Have we denormalized the data? And I would like to know the growth rate of the data in that particular feature or product. And I would like to understand which operations must be atomic in nature or siloed out, so that they complete fully or they fail fully. Yeah. And the personal data retention story that we are thinking through. If there is PI information, how would we retain? And for that, do we need SQL or a NoSQL kind of a database? Uh, Ideally, we should be pressure testing this using all the questions that we just stated, and not designing it until this is all clear. Yeah, that's how we should look for in a schema review. Imagine a senior leader asks, what is caching? We should tell it like this: instead of computing an answer every time, we can calculate it once, store it, and pull it up whenever we need it again and again. We looked at attention in LLMs, and how O of n square is a very complex operation, and to solve that we use KV cache on top of that at the inference layer. So whenever we generate one token, we pick that, put it in KV cache, and for the next token, we read it from the KV cache, the existing token, give it, and predict the next token, and so on. This loop goes on again and again and again until we have all the tokens for that sentence or paragraph or response. So one metric that we will usually measure with is the cache hit rate. If the cache hit rate is high, it means fewer expensive calls being made to the model or to the system underneath it. And the challenge is with the freshness. If a cache is a copy, so we need to build an invalidation rule to understand the staleness of the data. And why does the network often matter more than the model for latency? Because round trips are expensive on the hierarchy, because there are so many layers, and multi hops mean memory being spent at each of those layer. And even if it is sub-second model performance and there is 150 millisecond hops, it is a 1.5 second experience that we will see, not not a few milliseconds of models performance, but rather a 1.5 second experience. So we need to understand, hey, have we built a regional endpoints, have we done caching, have we cut down on the round trips that we are doing, and have we built streaming as an experience that provides better user experience. And that brings us to a close of part 2. All we need to understand through this session is, hey, which line of the 7 is the system performing poorly on, and that needs to be improved. We cannot just say, hey, how fast is the model. Thank you.